So today we are going to talk about compact models for MOSFET. These are done using a simulator called the SPICE simulator, which the full form stand for SPICE is Simulation Program with Integrated Circuit Emphasis. This is a general purpose circuit simulator. Is like having a CAD tool for the circuit design. So for any VLSI design project, it is important that one has a very sound knowledge of the physical models that are used to describe the behavior of the transistor, and also be aware of the various parameters that are essential for performing the detailed circuit simulations. And this is all needed towards having to arrive at an optimized design that you would like to employ for a particular circuit. So the SPICE has three built-in models. Level 1 called also MOS1, level 2 called MOS2, level 3 called MOS3. MOS1 is described by a square law current voltage characteristic. Level 2 is a detailed analytical MOSFET model, and level 3 is a semi-empirical model. Both the MOS2 and MOS3 also they include the second order effects like the short channel threshold voltage, subthreshold conduction, scattering limited velocity saturation, and charge controlled capacitances. So the type of model that one uses, or the level type of the MOSFET model that one uses in a particular simulation task, is declared on the model statement itself. So in addition, the user is also given the possibility of describing a large number of other model parameters used in the statement. They are related to the information about the geometry of a particular device, like the channel length, channel width, and the source drain areas. So a typical MOSFET element description line and model statements are shown here. This first is the element description line, where the M1 standing for the level 1 MOSFET model, the length of the channel, width of the channel, and the type of MOSFET that we are considering. In addition, generally many parameters like the V threshold, transconductance, CBD, CBS are also given, including some other parameters. So this table here is the model parameters for MOS transistor, where the keywords that are used for each of the parameters, like the zero bias threshold voltage, is represented by VTO, where the symbol stands for V subscript TO. It is the same symbol which is used for all the three levels. Its default value is given, and also its typical value is given, along with the units used for each. So the various parameters, you have the transconductance parameter Kp, given designated by Kp, gamma the body effect parameter, phi the surface inversion potential 2phi, the channel length modulation designated by lambda, Tox the thin oxide thickness, and N sub the substrate doping, then surface density by NSS, NFS Fs is the surface fast state density, and N effective is the total channel charge coefficient. As we will see later, these are often these three NSS, NFS, and NFF are used as fitting parameters. So for each one, the default values to start with are 0, 0, and these are the typical values that one gives. Besides these, you also have the parameters for the parasitic effects like IS, which stands for the bulk junction saturation current. JS stands for the bulk junction saturation current per square meter. Okay, and similarly you have these other values like the gate bulk overlap capacitance per square meter, designated by CGBO, CGDO, the gate drain overlap capacitance per meter, and CGCSO, the gate source overlap capacitance per square meter. So here we see a typical equivalent circuit structure for NMOS level 1 model. So this is the default MOSFET model used in SPICE. This basic structure is also employed for the level 2 and level 3 models. So here you see the voltage controlled source ID, which determines the steady state current voltage behavior of the device, while as you have the voltage controlled nonlinear capacitances connected between the terminals that represent the parasitic oxide related and the junction capacitances. Similarly, you have the source substrate and drain substrate junctions, which are reverse biased under normal operating conditions and are represented by these ideal diodes in the equivalent circuit. Finally, the parasitic source and drain resistances are represented by RD and RS, connected between the drain current source and the respective terminals. The basic geometry for the MOS transistor can be described by specifying the nominal channel gate length L and the channel width W, both of which are given in the first element description line. And by definition, this channel width W corresponds to the width of the area covered by the thin oxide. The effective channel length LF is defined as the distance on the surface between the two diffusion regions, namely source and drain. So to find this effective channel length, the gate source overlap distance and the gate drain overlap distances are subtracted from the nominal gate length specified on the description line. And this the amount of the gate overlap with the source and drain is given by a parameter called the lateral diffusion coefficient, that is LD in SPICE. So the same parameters are used for the P-channel MOSFET, only the direction of the dependent current source as well as the polarities of the terminal voltages, the direction of the two diodes representing the substrate, source substrate and drain substrate junctions are reversed. But the equations that are applied to the P-channel MOSFET are also of a similar kind. So now we look at the model equations for level 1. Level 1 is the simplest current voltage description of the MOSFET, and it is based on the gradual channel approximation. It's a quadratic model which was first proposed by Sinchman and Hodges. The equations used for the level 1 N-channel MOSFET in the SPICE are given as follows. First, the drain current in the linear region is given by K prime by 2 into W by LF, where W is the width of the channel, L is the effective length channel, into twice of Vg minus Vt into Vds minus Vds square times the channel length modulation formula, where this is the channel length modulation parameter lambda. These equations are valid for Vgs greater than Vt and also for Vds less than Vgs minus Vt. Next, we look at the saturation region, where the current is given by Id is equal to, this is a similar part as in the linear region, into you have Vgs minus Vt whole square into 1 plus lambda Vds. This holds true once again for Vgs being greater than or equal to Vt, but here Vds is greater than or equal to Vgs minus Vt. And the expression for Vt is given as Vt is expressed in terms of V threshold initial plus gamma, which is the body effect parameter, into root of twice of Fermi inversion potential plus VSB, the substrate bias voltage, minus root of 2 phi f. So the effective channel length L effective, which is used in these equations, is given by, as we had said, the channel length, gate channel length, minus twice of LD, where LD represents the diffusion length, okay, gate source overlap diffusion lengths. Next, the channel length modulation. The channel length modulation term is given by 1 plus lambda Vds, which appears both in the linear as well as in the saturation region, though the actual physical channel length shortening takes place only in the saturation region. So why this is included in both the linear and the saturation region is because it is included in the linear region as well, is to ensure the continuity of the first order derivatives at the boundary region, and that boundary region is the linear saturation region boundary. Okay, so the 5 electrical parameters that completely characterize this model are given by the transconductance Kp, threshold voltage Vto, gamma, twice of phi, and lambda. So these parameters are either directly specified in the model statement, or some of them can also be calculated from the physical parameters using these equations. So for instance, transconductance can be calculated by knowing mu and Cox. Cox is given by epsilon ox by Tox, and gamma can be computed from the knowledge of, once again, the permittivity dielectric constant of silicon, knowledge of charge. Na is the doping density, and Cox. Similarly, the surface inversion potential is estimated by the knowledge of the temperature and the intrinsic doping density and the acceptor atom doping densities. It is also possible to specify the physical parameters mu, Tox, and Na in the model statement instead of the electrical parameters, or you can specify both the physical parameters as well as the electrical parameters. But if a conflict occurs, for example, if both electron mobility and the electrical parameter transconductance are specified in the model statement, what will happen is that the value of the electrical parameter, in this case K prime, will override the physical parameter. So next we look at the typical variations of the drain current with model parameter VTO for level 1 model. So here is a plot of ID versus VDS for different VGS voltages, and where we are the parameter that we are changing are the V threshold, which from 1.2 volts to 1 volt, and the nominal parameter values used in this simulation are given here alongside, where the transconductance parameter is given as 27.6 microamps per volt square, and this is how it's designated in the element description line as 27.6 U. V threshold is given as 1 volt, it is just designated as 1. Gamma is 0.53 root of V, which is just written as 0.53, and the surface inversion potential is given as minus 0.58, written as 0.58. Lambda is equal to 0, which is given here. The corresponding physical parameter values which may be overridden by the electrical parameters are also listed here, like the mobility mu n, which is given in centimeter square per volt second, TOX as 100 nanometer, doping density as 10 to the power 15 centimeter cube inverse, and the diffusion length parameter which is 0.8 microns, so which is designated, the units are designated here accordingly. So also these are similarly the typical variations of the drain current with the electrical model parameters like transconductance, TOX and lambda for the level 1 model. So the first graph here is ID versus VDS for at different VGS values, where you are looking at the variation of the transconductance from 29.3 to 34.6. Similarly, the second graph is looking at the variation on these characteristics by varying TOX from 120 nanometers to 100 nanometers. And then you have the third graph which is looking at the variation of the lambda, which is the channel length modulation parameter, which is varied from 0.02 volt inverse to 0 volt inverse, where you are not considering any channel length modulation, whereas here you consider some small channel length modulation, and you can see that there is a significant change when you are including the channel length modulation in the IV characteristics. Next, we look at the level 2 model equation. So the basic structure is the same, but what now changes for the level 2 model equations in order to obtain a more accurate model for the drain current, we need to remove or eliminate some of the simplifying assumptions that were made in the original gradual channel approximation analysis. So first is that the bulk depletion charge has to be calculated by taking into account its dependence on the channel voltage. So then we will solve for the drain current equation using the voltage dependent bulk charge term, and this is given by this equation here. As you remember this, we had discussed this. If we do not ignore the variation of this bulk charge term as a function of x in the channel, then we can get this is the additional term that we obtain to be included in the expression for the ID current. So here FB denotes the flat band voltage of the MOSFET. The corrective term for the channel length modulation is present here in the denominator in this current equation. So this above model equation includes a variation of the drain current with the parameter gamma, even if the substrate to source voltage VBS is equal to 0. So we have included this body effect parameter even if we consider VBS is equal to 0. So the saturation condition is reached when the channel inversion charge at the drain end becomes equal to 0. So from this definition, then the expression for the saturation voltage VDSat can be calculated as given by VDSat is equal to VGS minus VB minus twice of the surface inversion potential plus gamma square, the body effect parameter, into 1 minus root of twice 2 by gamma square into Vg minus Vfb. So the saturation mode current is given by Vd is equal to ID sat into 1 by 1 minus lambda VDS, where ID sat is calculated from the above equation using VDS is equal to VD sat. So accordingly, this plot here shows for level 2 the drain current versus VDS for different VGS values by considering the variation with respect to gamma. Okay. So these are the various parameters that are given here, NB, gamma, and for the other curve it is slightly twice of what was used here, and gamma is also accordingly modified. So you can see here, because of these changes, the change that you observe is more accurate as compared in the previous, where we saw significant changes between the ID-VDS characteristics on change of a specific parameter. So the zero bias voltage VTO corresponding to the level 2 model can be calculated from the equation 8, which we had discussed previously, and it is given by this expression given here. So VTO is equal to phi GC, where phi GC denotes the gate to channel work function difference, minus Q into NSS by Cox, where NSS is a fixed surface charge density. So it is used like a fitting parameter also sometimes. So level 2 yields more accurate results than the simple level 1 model, but still its accuracy is not sufficient to achieve good agreement with the experimental data, especially for the short and narrow channel MOSFETs. So in order to overcome these deficiencies, there are a number of semi-empirical corrections that need to be added to the basic equations, once again with the view to improve their precision. So some of these enhancements are discussed now. One is related to the variation of the mobility with electric field. In the current equations that were presented above, the surface carrier mobility has been assumed to be constant, and its variation with the applied terminal voltages has been neglected. So this is actually not true, because the surface mobilities may get changed as you are changing the applied terminal voltages. So the approximation simplifies the calculation of the drain current integral, but actually the surface mobility decreases with increasing gate voltage. Okay, the surface mobility will decrease with increasing gate voltage. So in order to simulate this mobility variation, which is primarily due to this, and why do you get the mobility variation? This arises due to the scattering of the carriers in the channel. The modeling of the parameter K prime is modified then as given in this equation. K nu, or the transconductance parameter nu, is given by the K transconductance parameter into dielectric constant of silicon divided by the dielectric constant of the oxide layer into TOC into UC by VGS minus VT minus UT by VDS. So what does UC represent? UC represents the gate to channel critical field. The parameter UT represents the contribution of the drain voltage to the gate channel field, and this whole expression is to the exponent of UE, where UE is an exponential fitting parameter, and generally UT is chosen between 0 to 0.5. So this formula, this allows a good agreement between the SPICE simulations and what you observe from experimental data for the long channel MOSFETs. Next, we look at the other parameter, variation of channel length in saturation mode. So both level 1 and level 2 model equations use the empirical parameter lambda to account for the channel length modulation effect in the saturation region. Level 2 model also offers the possibility of using physical expression for calculating the channel length in the saturation mode. So the effective channel length is given by this factor delta L, by which it is reduced. So L effective minus delta L, where delta L is given by this expression in terms of the dielectric constant doping density Vd minus Vd sat. So this empirical channel length shortening or the modulation, the coefficient lambda, is not specified in the model's statement. Instead, its value is found by using this expression, where lambda is given by delta L divided by L effective into VDS. So if you are looking at the IDS VDS curve, the slope of the IDS-VDS curve in saturation can be adjusted and fitted to experimental data by changing the substrate doping parameter Na. So in this case, however, other Na dependent electrical parameters which are dependent when you change this substrate doping, there will be some other electrical parameters which will also get modified, like the surface inversion potential and gamma must be specified separately in the model statement, since Na is being used as a fitting parameter for the saturation mode slope. Okay. Then another parameter that we look at is the carrier velocity, the saturation of the carrier velocity. The calculation of the saturation voltage VDSAT is based on the assumption that the channel near the drain becomes zero when the device enters into saturation. This hypothesis is actually incorrect, since a minimum charge concentration greater than zero must exist in the channel, due to which you have a small saturation current. So these carriers will sustain that saturation current. The minimum concentration depends on the speed of the carriers. Moreover, the carriers in the channel usually reach the maximum speed limit, that is, their velocity saturates before the channel charge approaches zero. So the maximum carrier speed in the channel is denoted as Vmax. The inversion layer charge at the channel N, that is for VDS is equal to VDSAT condition, can be found as Q inversion is equal to IDSAT divided by the width of the channel into the velocity of the charge carriers, denoted by Vmax. The value of the saturation voltage VDSAT can also be found from this expression, and if the parameter is specified in the model statement, the amount of channel length modulation, that is delta L, in the saturation is calculated by the formula given here. So delta L is XD into Vmax by twice mu plus Vd minus Vdsat minus XD square minus Vmax 2 by mu. So this is to calculate the shortening, channel length shortening. So XD is given by this, where the XT parameter is given by this equation here in terms of the dielectric constant, doping density, and N effective. So here now N effective is a fitting parameter once again. So this model once again provides good experiment with the experimental data for the long channel MOSFETs. So, but to implement this is a bit complicated, because one has a discontinuity in the first derivative in the saturation region boundary. So this difficulty sometimes leads to convergence problem when you are doing these derivatives in the Newton-Raphson algorithm related to the taking the derivatives. Next, we look at the subthreshold conduction. This basic model is implemented in the SPICE. It calculates the drift current in the channel when the surface potential is equal to or larger than 2 phi f in the strong inversion region. So in reality, there is a significant concentration of electrons exists near the surface, even for VGS being less than VT. Therefore, the channel current, there is a channel current even when the surface is not in strong inversion. So this subthreshold current is mainly due to the diffusion between the source and the channel. So the model implemented in SPICE introduces an exponential semi-empirical dependence of the drain current on VGS in the weak inversion region. So this is given here. The voltage V on is defined as the boundary between the regions of weak and strong inversion, ID. This is the exponential expression dependence which is included, and here I on is the current in the strong inversion for VGS is equal to V on, and the voltage V on is found by this expression Vt into NKT by K, and where N is given by 1 plus Q NFS Cox plus CD by Cox. So the parameter NFS is the number of fast superficial states and is once again used as a fitting parameter which determines the slope of the subthreshold current voltage characteristic. CD here corresponds to the capacitance associated with the depletion region. And so from this we can see that the model introduces a discontinuity for VGS is equal to V on. Therefore, the simulation of this transition region between the weak to the strong inversion is not very precise. So here we are looking at the ID VGS characteristics for the level 2 model in the weak inversion region as a function of for different values of NFS. So these are the voltages for which this calculation is done, and we are looking at the changes in these parameters. So next we come to the level 3 model equations. The level 3 model has been developed for simulation of short channel MOS transistors, and it represents the characteristics of the MOSFET for channel lengths down up to 2 microns. So the current voltage formulation is the same as we do for the level 2 model. However, the current equation in the linear region is simplified with the Taylor series expansion of the main equation that we discussed in the level 2. So this approximation allows for the development of more manageable basic current equation compared to those of level 2. So the short channel and other small geometry effects are introduced in the threshold voltage and the mobility calculation. The majority of the level 3 model equations are empirical. So the aims of this using the empirical equation instead of the analytical models is to increase the accuracy of the model and to limit the complexity of the calculations. So therefore you are also reducing the simulation time. So the drain current in the linear region is given by this expression mu x into Cox and W by LF into VGS minus VT minus 1 by FB by 2 into VDS times VDS, where FB is an empirical parameter given in terms of gamma body effect parameter, Fs and Fn. So this parameter Fb expresses the dependence of the bulk depletion charge on the three-dimensional geometry of the MOSFET, and the parameters Vt, Fs and mu s are influenced by the short channel effects, while as the parameter Fn is influenced by the narrow channel Okay, so Fn is related to the width, and Vt, Fs and μs are related to the length, short channel effects. So the dependence of the surface mobility on the gate dielectric is simulated by using this expression, where the mobility Fs is described in terms of mu into 1 plus theta Vgs minus Vt. The level 3 model includes a simple equation that accounts for the decrease in the effective mobility with the average lateral electric field. So this is how the effective mobility expression is given, where μs is calculated. Okay, so from this you can calculate the surface mobility μs. The model for the weak inversion is the same as you are using for the level